It's a pleasure to be here today to present this lightning talk on machine learning operations. So I want to start by thanking all the people on the screen that have been a part of this project to date. So Digital Earth uses remote sensing machine learning models in our terrestrial environment suite and has been undergoing step change improvements in how we do MLOps. So our first focus was to focus on the right-hand side of that diagram, and that was on improving how we do our machine learning processing pipelines. And that was followed then by making improvements to the left side, which is around how we train, release, and develop our machine learning models. So one product in particular that has undergone this transformation is our land cover product. So that's an annual land cover classification for Australia. It uses 3 machine learning models: random forest regressor for woody cover, random forest classifier for cultivated vegetation, and convolutional neural network deep learning for artificial surfaces to assist in classifying the landscape into distinct land cover types. So this product is freely available for everyone to use. So our first step was to have our code redeveloped and refactored into modular components or plugins. And so that's so that we could make intermediate products for each of our machine learning models before aggregating them together into our level 3 and 4 outputs. So we used Argo Workflows, which is an open source container native workflow engine for orchestrating parallel jobs in Kubernetes to this transformation. And this enabled our machine learning process to become reliable and scalable. The plugins were integrated into the Open Data Cube statistician environment, and that's a framework for flexible tools for generating statistical summaries of large collections of Earth observations imagery, and these plugins are available for everyone to use as well. Although we had validation data sets for each machine learning model, we found that some of those misclassifications were only picked up when we did our large-scale continental comparisons that were run through ODC stats. Some of the benefits can be seen in this animation between version 1 and version 2 of our land cover product, in particular for our artificial surface classification. So through continental iterations, we were able to fine-tune the results and reduce some of the misclassification between natural bare surfaces and artificial surfaces. And similar for cultivated area and woody cover, you see in those 2 diagrams. And then lastly, we then focused on improving how we train, tune, and release our machine learning models. So we put together a proof of concept for our artificial surface model, and we moved the machine learning training from being notebook-driven to being pipeline-driven. And so we used a SageMaker, Elastic Container Registry, and Bitbucket pipelines for that piece of work. So model training moved from running on single large nodes to being scaled to multiple pods and nodes. And that enabled for much more optimized hyperparameter tuning and provided us with a 70% cost reduction and a 60% runtime improvement. Our parameters for tuning models were elevated out of the notebooks into a config-first pipeline-driven design and made things reproducible and portable between environments. We used MLflow, which is an open source tool designed to manage the life cycle of models and provide a capability for tracking experiments, packaging code, and managing models. The proof of concept used DVC, data version control for automated versioning of data inputs and outputs, and the infrastructure was deployed using Terraform, TerraTest, and LocalStack. And if you want to chat further about anything discussed, you can find me down at the booth downstairs. Thank you very much.